And then now I guess we can turn it over to Colin and do kind of a walkthrough on our new Project Swordfish, which is going to be the new execution engine in Daft. So I guess Colin, over to you.
I'm just going to give a quick update on Swordfish. So yeah, what's Swordfish, right? Swordfish is our project, is the name of our project that we're gonna revamp our new local execution engine. Right now, if you didn't know, Daft has two engines, a local one that's based in Python and a distributed one that uses Ray. And so we're revamping our local one to port everything over to 100% on the Rust side. Additionally, we're going to change the architecture slightly to it's going to become a streaming push-based engine. The overall goals of this project is, better performance on a single node. If your data is in the 10 gigabyte range or 30 gigabyte range, something like that, we really want to make running that on a single node really performant for you. We want to improve observability. We're going to add a bunch of different features that allow you to dive deep into how Daft is executing on your local machine, seeing things like how many rows each operator received, how much time it took, and seeing things like, explain, analyze graphs, and even Chrome trace diagrams. Yeah, so let me dive deep into basically, the before and after of Daft's local execution engine. So before, um, Daft is a pull-based volcano-style execution engine. So partitioning and parallelism is baked into your logical plan. For example, if you had, if you're reading five files, chances are you're going to have five partitions, and these five partitions are going to execute in parallel across your node. If you did something like into partitions or repartition, that also affects parallelism, and it's in the logical plan. And additionally, each operator will wait for its input partition to fully complete. So for example, if you're reading one single file and you had a lot of downstream operations like filters, projects, or aggregations, your entire file will be fully materialized into memory before any of its downstream operators even start. And this can cause basically inefficient memory usage because we actually want to do, those downstream operators whenever we receive, chunks of data. And so that's kind of the rationale behind the new streaming engine. Partitioning is now dynamic. It's driven by morsels, which are basically the number of rows or bytes that we read from the source. And morsels are emitted to downstream operators whenever they are ready, which means we do not need to wait for your file to fully be into memory before we can start executing downstream operations like filters, projects, or aggregations. And this leads to much better memory usage, which I'll show you guys a little graph later. Now on to some results. So our new native engine is actually much better already than our Python-based engine in terms of the TPCH benchmarks. You can see we're reaching on some queries, 2x speedups, and on some other queries, maybe like 10%, 20%. Of course, it's not fully complete yet. You can see here on Q8 that select queries is still a bit slower, and that's because we don't have the best statistics propagation in the native execution yet, and that's something that we're actively working on. And then onto the memory part, I think this is where it gets really interesting. You can see on the native side, we're pretty much on all queries hitting much less memory usage compared to our old Python runner on the TPCH benchmarks. And like I said, this is because of the new streaming execution, where we're able to pipeline operators before fully materializing their input partitions. And this allows us, especially for cardinality reducing queries like aggregations, it really allows us to drastically reduce the memory usage. A neat little graph here that actually shows you this query is TPCH Q6. It's essentially reading from a file and performing a sum aggregation on it. And you can see that the streaming execution, which is the top graph here, is only reaching 250 megabytes total heap size compared to the Python runner, which reaches more than 400 megabytes. And this is basically because we're performing the aggregations as we read in chunks of data from your file. And because of this, we're reducing the total amount of memory that we're consuming in the engine.
Yeah, and I guess Colin, to point out here in the bottom graph, it's like reading the file and then it
Mhm.
spikes when we're doing the aggregation, right? So
Yes.
it's like reading the entire file before that spike at about 154617, and then it
Mhm.
spikes when we do the big aggregation. But then for
Mhm.
the top graph, we're like, as we're reading the file, we're reading small chunks of it, small chunks of data, and we're doing the aggregation as we go along. And so the total amount of memory that we have to use then isn't nearly as large, and we don't see that same big spike.
Yeah. Essentially, like Jay said, you can tell, oops, in this graph, this is where, your file has been fully materialized into data and aggregations haven't even started yet. You can see the heap size goes down because we're starting to do aggregations. However, on the streaming side, we're actually performing aggregations while we're reading your data from memory. So it will never reach, your data will never fully materialize into memory. And you might be wondering, oh, how do I know that it's actually doing the aggregations, right? You want to see, where and when and what operators are taking place, in this new stream execution engine. And so one of the things that we implemented to enable this kind of observability is tracing. Um, and so this is the exact same query. Oh, no, this is a different query. This is a different query, but it shows kind of the same streaming execution that we were talking about, where we can read in your data and perform downstream operations in parallel because we're pipelining these operators. So you can see here that this is a hash join query. There are some hash joins here and so forth. And these pink things are basically your sources. So while we're reading the sources, while they're still completing, we're actually doing hash joins. And this allows us to basically drastically reduce the amount of memory that's needed. In the past, if you were to do this with our Python runner, you'd see a long line of just process scan test stream and nothing else, and then all the hash joins starting to work. And that will basically fully materialize your data into memory, which is highly memory inefficient. Another thing that we're implementing with this new local execution engine is um, tree graphs like these, where you can actually see the operations and the operators that are taking place. And for example, you can see how many rows were emitted from a scan task, how many bytes were read, how long it took the project to fully complete, which side we're building a probe table on for hash joins, which side we're probing on, how many CPU seconds these operations are taking place. And so all these visualizations and observability will be available with the new local execution engine. And so our roadmap. Um, so the native executor is not fully functional yet. We still have a few operations to complete, and we still need to enable 100% test coverage, but it's still working. It is working right now for basically most of the most common operations, aggregations, joins, sorts, um, all the reads from files. These will be available to you right now with the environment variable. You can just set Daft enable native executor equals 1, and this will be available to you. We're hoping to release a beta that's fully working Swordfish by September, and then fully replacing our existing Python runner with Swordfish in October. In order to do that, we need to achieve 100% test coverage. I'd say we're basically at maybe 85, 90% right now. In addition, we need to implement much better statistics for smarter queries. Because this is a streaming engine and we don't fully materialize partitions, we need to rely a lot on statistics in order to determine how we order our queries and, for example, which side do we want to build a hash table on for hash joins. In the past, we'd fully materialize both sides, and then that's how do we determine which side to build. But we can't do that anymore. So we need to build out more efficient statistics propagation. Additionally, once all this is complete, we're intending to port Swordfish over to the distributed execution side. So you can imagine on your cluster of nodes, each node will be running, a little mini Swordfish. Um, Yeah. So that's the roadmap.
Yeah, I guess like what are some interesting workloads you can call it that will be benefiting storage? I have one on top of my head, which I usually do, which is like you read from Parquet and then you run a URL download on like a column of URLs, right? So you
Mhm.
materialize all the URLs into memory, and then you do something like image decode to decode it into images, and then you resize the image and then maybe like spit out a tensor and save it somewhere, right?
Mhm.
So today, at least, what will happen is that for basically for every Parquet file, we will end up downloading all the URLs, say maybe like, I don't know, like 100,000 URLs, right, into one giant partition. And then that takes up all the memory on the machine. And then it like proceeds partition by partition, like image decode, and then like, resize and then whatever. But in the new world, I think what's really cool is that you go end to end, right? You go from reading the Parquet, you spit out little bits of URLs, you then run those URL downloads, and then you move that little bit of data over into image decode and then even into the write at the end. And so you get this super streamlined memory usage across from the read all the way into the big inflations like URL download all the way down to the writes. That I think is going to be really interesting. Are there any other workloads you think that off the top of your head that will like be benefiting the most from streaming execution?
I think recently we had someone basically use this to do like a data export. And I think basically any kind of like exporting where you're reading from some source and then writing to another source will really benefit from this. Because essentially with the streaming execution, we can pipeline all your operators. So once we read, for example, a chunk from your Parquet file, the next step is the write. And the write is going to happen concurrently with all the rest of the reads. And so your memory usage will never basically reach the total memory of what you're reading from with this execution engine. So I think, use cases like that will really benefit from this new execution model.
I guess cases where the sink is some like remote thing, like piping
Mhm.
data to a sink, right? And you don't need that
Mhm.
data anymore in your system.
Yeah.
And it's like completely streaming all the way down.
Yeah, exactly. Yeah.
Cool. Do you have any more questions from the crowd? If not, then yeah, I guess that concludes our community sync today.